Alrighty everyone, good evening. It's my first video, the QCE guy, and well, let's get ready to roll. I've got the doggo on the bed. I'll flick over to him just down there in the corner, and yeah, well, look, lovely good evening to you. Today we're doing the complete Chem crash course, so hopefully it's an enjoyable experience for you. And I'm going to cover through as much as I can regarding chemistry and what we've covered in Unit 1. I think that's enough being said. Let's get further ado. Alright, so today we are going to be looking at, I'm just going to fix that camera up real quick. We're going to be looking at properties and atomic structures, analytical techniques, periodic table trends, and bonding. So I'll get into those very, very briefly, but properties, including but not limited to how atoms react, what atoms are made of, all sorts of kind of things like that. Analytical techniques using like mass spectroscopy, flame testing, stuff like that. Periodic table trends, which will be atomic radii, ionic radii, electronegativity, first ionization energy, so on and so forth. And lastly, we have bonding, which, I don't know, if you don't like bonding, you don't like bonding. If you like it, you like it. But hopefully I can make it enjoyable to everyone. But yeah, let's move on. Properties of atoms. So, it's pretty much, atoms are really interesting. So, they are the fundamental part of life, and they make up pretty much every single molecule. There are particles smaller than an atom, such as like the electrons and the protons and neutrons, but honestly, the atom is pretty much where it all begins. And it's some pretty exciting stuff too. So they make up everything. They make up me, they make up apples, they make up xylophones. I couldn't really think of anything that started with Z on the spot. But yeah, they make up anything. Your water bottle, or your notebook, or your pen, or anything. Even you who are watching. And then in the nucleus, in the central nucleus of the atom, this is what I was about to say. There are neutrons and there are protons. Where neutrons are like these little, tiny, right? Tiny little particles, and they have no charge. And protons are also really small, but they do have a mass. Both neutrons and protons have a mass. And this mass is one atomic unit, which we'll get around to how that works in a minute too. But one atomic unit is what makes up a neutron and or a proton. And these are held together in like where's my camera? They're held together in like the center of the atom, and they're quite like tightly bonded in. And then around them, you have electrons, right? And these electrons are like little negative, they're tiny. They're, I think, 1/2000 of the mass and size of a neutron and or a proton. And if you want me to put that into like a size equivalence for you, one electron is pretty much the size of like a tennis ball compared to the GABA, like the football stadium, the GABA. I think that's right. Anyways, it's about the same size as a football stadium. But anyways, yeah, these electrons, they can appear on like distinct energy levels. So like your first shell, your second shell, your third shell, your fourth shell, so on and so forth, up to the seventh. And on these shells, you have these atomic orbitals. And orbitals are like where the electron is most likely to be, like in a probability sense. So you have an s orbital, which is on your first shell, then your p orbitals, they start from your second, your d from your third, and your f on your fourth shell. And they're kind of demonstrated here with all the different probability spots where they can be. So they can exist in both s, p, d, and f orbitals at the same time. Pretty exciting. Well, what's what? Let's find out. So in chemistry, we often use symbols to make things like a lot simpler to understand. Similar to math, how you might use Q for rational numbers, or you might use R for real numbers, I for irrational, so on and so forth. So in Chem, we use Z for atomic number. And a nice way to remember atomic number is it's the number of protons. So if you're ever stuck, just think, right? Oh, lithium, hydrogen, helium, lithium. So you've got 3, okay? It's the third number on the periodic table, and it's also going to have 3 protons. A, the letter A, is used for mass number. And a good way for remembering that is A is for atomic mass. And you can determine that by summing your protons and your neutrons together. And if you find M, it's not too common, but you might find it in a certain notation. M will be used for a placeholder for like an element symbol, which will normally be written shorthand. So you would have seen K for potassium, I've got Ar for argon here, Ne for neon, so on and so forth. Which way can I orient this just to be a little bit more on center? Here we go. Isotopes. So, isotopes use some of these letters from the previous slides, such as Z, A, and M, and they're written this notation here, which I'll get to in a minute. I'm sorry for it being off center. I was working with it earlier, but it decided to play funny bugger on me, so apologies. But isotopes are pretty much the element, right? So you'll have an element, and it'll be having a different number of neutrons to it than to its protons. So the different number in neutrons actually can affect the properties of it, the physical properties. So it'll bond the same, like I've got protonium, deuterium, and tritium here. So for example, you know how water is H2O? It's still going to form that bond, but instead of it being H2O, it'll be D2O for deuterium. These are the only elements that change. Everything else, it will stay H2O or MgO if it's like magnesium oxide and so on and so forth. But you will never really have to deal with isotopes in bonding yet. I think that's university level or if not beyond, so don't worry too much about them. But they will have different physical properties. So they might be more dense due to that extra neutron, like that will affect the density, even their effective nuclear charge, how well they are, if they are radioactive, so on and so forth. And often, it's hard to see here, but they are written as AZM, where A, as we said before, is the atomic mass, Z being the atomic number, and M being the atomic symbol. And in order to determine the protons, the neutrons, and the electrons, you can use the number A on top, and you take away the number Z, and that will give you the number of neutrons, and the number Z will also equal the number of protons. And in a neutral atom, which would be the case for an isotope, unless it's got like a 2+ or a 2- or whatever, those number of protons will be equal to the number of electrons. Electron orbitals. Let's keep moving, bro. Let's keep moving. And the rules and what they are. So, what are the orbitals exactly and the energy? So, I kind of briefly went into this on the first couple slides. But orbitals are like pockets, you can imagine, right? Like they're little, so like you've got like the nucleus here, and then you might have like a pocket like this. So you might have one that comes out here, one that comes under, and then one that comes out on either side. And then, yeah. And pretty much that's where the electron is most likely to appear if they were observed. And within the orbitals, they are confined to 4 like levels. And I've sorted them by lowest to highest energy for you here. So you have the s orbital, the p orbital, the d orbital, and the f orbital. And the energies of these orbitals start on the s orbital. So every shell, like shell 1, shell 2, shell 3, shell 4, which is equal to the period you're on, right? So like, you know how hydrogen and helium share the same period? That's the first shell. And then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, that's the second period, and all those electrons are going to be on the second shell, if you can understand that. So p orbitals will be on every single shell following, but not the first one. D orbitals will be on every shell following, excluding the first and second, and f orbitals are on the third shell and beyond. But in year 11, I believe the f orbitals are irrelevant for drawing diagrams. So you'll mostly be focusing on sp, and a couple of elements will be in your d orbitals too. And the rules of orbital filling are quite important in chemistry. So I'll go through them quite quickly now. There are a couple of rules to make sure it all goes steady, well, and effectively. And in order for you not to lose any marks, I do not want you losing marks because you misplaced an orbital. Please, for the love of God, don't do that to me. Anyways, you have the Aufbau principle, which is asking you to fill the lowest energy level shell first. So the lowest energy shell level, if we have a look at the chromium example, right, you should be filling this orbital first. That's the lowest orbital, okay? Then the next order you should be filling should be this orbital, and then so on and so forth. This is pretty intuitive, and I think it's pretty hard not to stuff that up. The Hund's rule is you should fill individual orbitals, then make the pairs. So the Hund's rule is pretty much saying for one orbital, you should do that arrow first, then you should do the down arrow next. Then this one, you should do the up arrow first, down arrow second. Then this one, this is where it starts to get interesting with Hund's rule. You do up arrow, up arrow, up arrow, and if you still have electrons to fill, you do down arrow, down arrow, down arrow. So it's pretty much asking you to fill each individual orbital first before making an orbital pair. The Pauli exclusion principle should also be mentioned, where the electrons inside of these orbitals should not have the same spin. So see how they've got up and down arrows, right? That means that one electron would be spinning this way, where's the camera? Coming towards you, spinning, and the other one's going to be coming towards me. Whereas if they were both going towards you, that's not going to happen just by laws of physics. So the Pauli exclusion principle makes sure that you pretty much abide by that, and you have one spin going that way, one going that way. And a quick thing that Miss White didn't cover, but I'll do it for you now. There are two exemptions to the rule with, I think it's the Aufbau principle, where copper and chromium hold exempt. So I've done a diagram here so it's a bit easier to visualize. So normally, most people assume that you fill the orbital level. Most people assume that you fill the orbital level as you go up one and then down one. But for the case of chromium, you're gonna give that extra electron to that 3D shell, and same with copper. So instead of it being 3D9, you're going to form 3D10, which will be complete. And instead of 3D4, you're going to form a 3D5. The next thing we're going to cover is analytical techniques. So we learned about this briefly too, with atomic absorption spectra, atomic emission spectra, atomic mass, and the more. So let's dive into it. Mass spectrometry. It's a very well-renowned device in chemistry, and I think even in the field of applied sciences, even biology to an extent, you can kind of use this. But what happens here is, first of all, you put a sample inside this like tube, and it's got a heater that will effectively vaporize it, which means to evaporate it into a bunch of particles that are disjoint from each other, and they'll be just completely broken, all the bonds in a gas state. And after this, it will ionize the sample. So it'll send a bunch of electrons into the sample, and in doing so, it'll ionize it as such, which will give it the charge. After it's been given a charge, it'll be sped up through an accelerator, run through the electric field, which will speed that up. So that's what the ion acceleration is. And then the magnetic field, so that the magnet, and pretty much the charge that the electrons have given it will affect where on that end plate it lands for the graph. So a positive charge is going to get deflected more than a negative charge. You don't need to know that, but you can kind of see it in the graph here, how the beams spread out on that plate. Sorry for the cameo being in a way. But yeah, so you have all that information, and pretty much the mass spectrometer records the data in the way that like where that individual element and the charged particles have landed. And the data is used in heaps of ways. So for year 11, we use it for determining the mass of a particle and its abundance. So you might be given an element, you vaporize it, and then it'll come out with 3 relative abundances and a mass. And then with that information, you can calculate its average atomic mass. And fun fact, the mass unit actually comes from carbon-12. And because carbon-12 has got 6 protons and 6 neutrons, it's the only element that does this, but it's got a perfect mass of 12.000 units. So if you divide it by 12, that will be the mass of like 1 proton or 1 neutron. But that mass is also equal to a mass unit. So that's how they got the like measure unit to record the weight. So you know how like uranium is like 235 AMU or mass units, right? That mass unit means it's 235 times greater than 1 particle of carbon-12. Anyways, this will be a fun fact for you. Okay, mass spectrometry graphs. So often after your mass spectrometry experiment I explained before, you'll be given a graph like this, and you should be quite familiar with it. So you can see at 24 m/z, which means mass to charge, okay? So 24 will be your mass. You can see at mass 24, 79% is the abundance, okay? And then at mass 25, 10%, mass 26, 11%. Now, all you have to do if you want to calculate the average mass is you multiply 24 times 79, and then you add that to 10% times 25 times 11% times 26. So you add those 3 multiplication values together, and then you divide it by 100, and that should give you your value. And the reason you divide by 100 is because see how you've got this percent here? You're trying to get rid of that percentage. So you divide by 100 in order to do so. Moving on, we have atomic emission and spectra. So atomic oh my god, atomic emission and absorption spectra. I forgot the absorption, I'm sorry. So atomic absorption is the energy that an electron will absorb and jump as such. So pretty much an electron will get struck by energy in some form, typically light. And when this happens, it'll jump up an energy level. And when this happens, that certain energy of light that caused it to jump up will be absorbed into the electron, and because it's done that, it will leave a black spot in the absorption spectra. And every element is unique in this. So you know how we were talking about the electron configuration before and the electron orbitals? That means that it'll be unique for where the atomic absorption happens. So it can, for hydrogen, I know it happens one in the infrared zone, one in the green zone, one in the blue zone, and one in the dark pink zone, the ultraviolet. But fluorine would be different to hydrogen, and they're all different to each other. And atomic emission spectra, so the other one. So you can see how we've got absorption here with the black lines, and then the black graph with the colored lines is emission spectra. So it's similar, but when the electron jumps back down, right, to original energy level, it'll emit that same length of energy that was initially absorbed. So that same length of energy will correspond to a light wave and its energy. You don't really need to know much like what energy causes what, but it's important you understand the theory behind it. And it'll jump back down and emit that photon, which will correspond to that color, being infrared, ultraviolet, whatever color, visible light. The other thing that's really useful with atomic absorption spectra is that it can be used to determine the concentration of a substance using a linear looking graph. So it will have absorbance on the side and then concentration on the bottom, and you'll be given a couple dot points along the graph, and you'll draw an equation, determine it, and then you can plug in your values for whatever the teacher will give you to make a prediction for it. Okay, flame testing. So flame tests work very similar to the way that atomic emission spectra also works, where the visible light is emitted by the electrons jumping down orbitals and emitting light. However, the flame test works only for visible light. So if I was to head back a page, I can't, sorry. You can see that there was one one wavelength that was visible, and that would be the color if you were to do a flame test to hydrogen, I think it was. What is important though is you just need to understand how it works, and you might need to memorize a couple colors. So lithium being like an orangey red, sodium being a bright yellow, potassium being like a lilac or a purple, rubidium pinky, cesium pinky, calcium burns a brilliant orange, strontium being a red, barium and copper, you can say bluish green or green, either or works for them. And iron is a nice red. I don't believe you need to know iron though, because it's got different charges, so it can change. One interesting thing though is the changing colors for a flame test actually proves that model of atom we saw earlier to be true, where the electrons are like in orbitals and they are separate to the nucleus. Because in previous models in history, it was believed that the electrons were all bundled in to the nucleus, whereas Bohr actually proposed that they were not, and they were like on separate energy levels, and that flame test proved it. Okay, periodic table trends. So I'm going to go through this quite briefly because we have done extensive amounts of work on this, but I have taken notes either way. Just would like to let you know. Reactivity. As you move across from the alkalis, so for example, lithium, sodium, I think rubidium is in there. They all have a valency of +1. That's a good way to remember the alkalis. So as you move from them across to the transition metals, which in our class they are like the orange metals on the the red metals on the periodic table, like iron, copper, nickel, cobalt, titanium, etc. So as you move from alkalis to those transition metals, they become less reactive. Like they're not going to bond nearly as much as they would if they were like alkali metals. However, the reactivity does begin to increase as that comes to an end and they come past the metalloids. Especially as they approach like chlorine and fluorine, where they have 7 valence electrons and they need just 1 more. So they are very reactive to get that last valence electron to make a full shell. Overall, I guess you could say the trend would be like as you keep moving across, it will decrease until like the ±4 charge occurs. And then as you head in like -3 directions, it'll just keep getting stronger and stronger until you hit -1. But the noble gases actually don't react because they've got like the full outer shells. Moving down a group, I forgot to write this in here, but the reactivity increases as you move down a group because they're easier to like lose off the electrons and they really want to just have full shells. I've gone through very quickly here, this is what I meant, but hopefully you can see what I mean. So the other trends that we'll need to know would be ionization energy, atomic radii, electronegativity, and they're all kind of represented in this table I found. You don't need to know about metallic or non-metallic character, and you don't need to know about electron affinity, but you can kind of understand why ionization energy increases as you move across because of the effective nuclear charge. The atomic radius decreasing as you move across because the effective nuclear charge pulls them in closer. As you move down a group, it decreases because there's new subshells being added. Yeah, and so on. So generally, most of the trends are controlled by the effective nuclear charge, which is like the pull that acts on those outermost electrons. So it's kind of impacted by the distance between the nucleus and the electrons too. But the effective nuclear charge is how strong that nucleus is going to be pulling those valence electrons to it. Other things that will impact it will be the number of shielding electrons. That also comes into play for effective nuclear charge, but that explains atomic radius. So the number of shielding electrons as you move down a group will literally be like a whole shell, right? Every time you move down. So that's why there's going to keep getting bigger and bigger, and that's why the radius will be bigger. And also the number of protons will affect the nuclear charge. So number of protons changing the effective nuclear charge, that will make certain changes in properties and trends too. One other keynote is valency. So like, you know, like 2 minus or 1 plus or 3 plus or whatever. That also plays a really, really big role for electronegativity, or how likely an atom is to attract electrons to it. So fluorine and chlorine are known to be very, very electronegative. Like they will like pull electrons into them, like no matter what cost it is. Whereas other atoms like lithium, rubidium, they really don't want their electrons and are trying to get rid of them. So they are considered very electropositive, not electronegative. Moving on. So we've got bonding with our old mate Lewis and his drawings, plus some metal, covalent, and ionic bonding types, which I'm just going to cover through now. So, what are bonds? So bonds are like an arrangement of electrons in atoms, and how stable an atom is kind of affects what bonds are formed. So ionic bonds are formed by the elements that form ions, whether they give or take electrons, and that will impact the type of bond. Covalent being where they share, metallic if they give off electrons. It all depends on how the electrons are arranged. And the number of electrons that is gained or shared or lost will be determined by the charge. Like, you know how oxygen is 2 minus and calcium is 2 plus. That's why it'll form CaO. But Na and oxygen requires 2 Na molecules. So you'll have Na2O because Na is only a single plus, but oxygen is a 2 minus. Ions are also really important, and how you treat them is like normal elements, but they have a lost or a gained charge. So if they've gained electrons, they have a negative charge. So chlorine, right, when it gains an electron, will have a Cl minus charge. Or when sodium loses an electron, it'll have an Na plus charge, because you can imagine it like it's gotten rid of a negative, so it becomes positive. Pretty easy to visualize that. And bonds, like as a group, are like a connection that's formed between 2 or more atoms, and it's like a glue. So that's what's really holding like water together, for example, like H2O, the bonds as such, where it's like a glue that's attracting them all together and quite like bonding them in a way. Lewis structures, okay. So I've just got a couple steps here to remind you of how to draw Lewis structures. I didn't really want to go into huge depth about this, mostly because it's quite easy to do once you get the hang of it. But I've just given you the steps here where you should, first of all, you should get the number of valence electrons. So carbon has a valency of 4 and oxygen has a valency of 6. So you should have 2 times 6 plus 4. So 12 plus 4 is 16. Then you should determine the number of electrons to fill shells. So you should go, okay, I'm going to need 8. So you're going to have 8 electrons for both oxygens and then 8 for carbon as well. And then you're going to choose your central atom, which will be carbon because it's the most, like it makes sense to put carbon there because the oxygens aren't going to really bond to each other like that. Just a note for that too, you should never choose hydrogen. Even though it might be the most electropositive, you should never choose hydrogen as your central atom. The next thing to do would be to draw your lines or crosses. I think Miss taught you guys how to do crosses, but I draw lines like how these guys have done it here in this diagram. And for carbon, because you want to satisfy, it's like 8 bonding pairs, you'll do 2 double bonds to the oxygen. In doing so, that also means that it doesn't need that double lone pair on either end. So that's why you've only got the last 4 electrons on either side of the oxygen. The ionic compounds that are formed are when elements have like formed a positive and negative ion, as I was talking about earlier, when they give off electrons or they take on electrons and they'll complete their full shell. And when they do that, they become like positive and negatively charged. And kind of like how a magnet works, how north and south are attracted, the positive and negative charge will also attract to each other. This explains why they have very, very high melting points, but they won't have any electrical conductivity. And that's because they don't have any electrons free flowing around because they're all stuck up in like the bonds. But they're also really, really strong because of their bonding structure too. But they aren't malleable like a metal. So you know how metals, if you were to like hit it, it kind of like bends in a bit. Whereas an ionic compound, like if you were to hit a crystal of salt, it would like shatter. Because it doesn't have like the sheets that would like slide in between each other and can adjust, as the bonds just won't support that. The ionic bond is generally known to be the strongest type of bonds through both intermolecular and intramolecular. Inter meaning like between, intra meaning inside. Covalent compounds. So a covalent compound is where two non-metals, like two oxygens, two hydrogens, or like Cl and nitrogen or something like that, where they'll share electrons with each other in order to complete their full outer shell. And that's why you often find covalent compounds as a gas. So if you have a look at CO2, that's always a gas. Cl2, like the two chlorine atoms, two oxygen atoms, two hydrogen atoms, that's why they're always a gas, because they have really weak bonds, and that also explains why their melting point is really low. These guys also don't conduct electricity like ionic bonds, just because they don't have any electrons that they can really just like give away for free, because they're all being used in the sharing. And effectively they've got like no real way of measuring strength, but their strength is because they're gaseous all the time, so you can't exactly measure that. And the two nuclei that are bonded, so like Cl2 for example, will have really strong attraction to each other, but it won't be as strong as an ionic bond. One of the last few things to go through is metallic compounds. So metallic bonding is caused by metals giving off electrons to be positive. So metals are like charged, not charged. Normally they're neutral, but they'll have like 1, 2, or 3 extra electrons on their valence shell, and they're just gonna give those off into like a sea. They call it a sea of delocalized electrons. And in there, all the positive metal ions, like after they've given off their electrons, are going to be attracted to the free-flowing electrons without grabbing them, but they will be attracted, which causes them to have quite strong bonds. The moderate strength bonds allow for their melting point to be like moderately or relatively high, and it also allows them to be ductile because they form like a sheet, and these like sheets of lattices like slide over each other because the electron and metal configuration doesn't really matter too much. And overall, the attraction between the nuclei and electrons is relatively strong because of their properties of strength. Intermolecular forces I'll go through quickly, and I think this is the second last thing, and then we've got carbon molecules left. I'm sorry for keeping you here so long, but I hope you found it useful. So, H bonds or hydrogen bonds are caused by a dipole, which you can imagine is like a charged end, okay? And these form on a polar molecule, meaning that like the molecule is like unevenly shaped or distributed in the way that it's orientated its like atoms and electrons. The hydrogen in this case kind of acts as like a positive dipole, and it will attract more electronegative atoms to bond with it. But these atoms aren't from the same molecule, they're actually from distant molecules. So it's quite a strong bond if you think about it. So let's imagine like CO2, right? And then you have H2O. Then those hydrogens are really going to attract that CO2 into it, and it's going to bond in an intermolecular way. As I was talking about dipoles with H bonds too, so you have another thing called dipole-dipole bonding, which is pretty much where a dipole, which can be positive or negative, depends on the atom that's on the molecule, will appear, and that will also attract the atom of the opposite dipole to it. So if a positive and a negative dipole meet each other, then they're gonna bond together through dipole-dipole attraction, which is kind of like ionic bonding, if you can imagine it like that. It really isn't, but it kind of is in a way. It's like positive and negative charges attract each other. And the last intermolecular force that we need to know would be dispersion forces. So these are where like a temporary dipole as such might be formed on a really large molecule. And this temporary dipole is going to orient the other molecules around it to be attracted to it. It's pretty much just dipole-dipole bonding, but instead of it being a permanent dipole, it will be a temporary one. And pretty much as the molecule grows larger, there's a more likely chance that the electrons are going to orient themselves in a way where the dispersion forces are going to occur because like dipoles are going to happen. Okay, last thing is carbon molecules. So carbon can come in many forms, such as like graphite or diamond, graphene, and you wouldn't have heard of this yet, but a fullerene. And you don't need to know that, it's just extra fun. It's kind of like a soccer ball shaped thing, kind of cool. But yeah, so you have diamonds, which are very, very strong. They're the hardest substance known to man, and they've got a really unique crystal lattice structure where all the carbon atoms are bonded to each other in like a 4x4 way, and all their bonds are utilized, which means all their electrons are also utilized. This full utilization explains their really high melting point, and due to that really high bond strength, they actually don't conduct electricity, because all their electrons are kind of seized up in a way into this diamond molecule. But oh my god, what else is really interesting is the graphite like network too. So graphite has like a hexagonal bond where it only uses 3 carbons to its 4. So it has a lone pair that's like free, and that's actually why it can conduct electricity, because these electrons aren't bonding to anything, so they're just kind of chilling there, and then they're allowing electricity to go through. And the structure of it being hexagonal is also quite strong, and a triple bond. Not triple bond, sorry, the carbon being bonded to 3 other carbons. So it's not as strong as diamond, but the melting point and like tensility, like the strength of it, is still really, really quite strong for most covalent molecules. So graphite is also really interesting. And it follows a similar property to metals in a way that the like sheets slide over each other if they get like whacked, which is why you can actually make graphite into your lead pencil, because it will be happy to like not malleate, like change its form to suit that shape that it wants to be, that pencil. Alrighty, and sorry for the long yap, but I hope you found the crash course useful. Thanks for tuning in to the Unit 1 review for chemistry with the TheQCEGuy, and I'm just going to keep publishing, keep posting, I'm going to keep working on it, and I hope you guys have a wonderful night, morning, day, or whenever you're watching, and Osh Geldeners, and see you later.